Hello students. Before actually starting the lesson, let's in the first two videos, let's briefly review whatever we have learned so far. Okay, so we were on module 3 and this is what we had done in the class. Since it's a review video, I am not going into the details of how we are doing it. I am not going to elaborate on the video. This is to just jog your memory and also a brush up of whatever we have done, so that if these concepts are clear, then only we can proceed further with this. Okay, we were on module 3, Maxwell's equations and optical fibers, review of the concepts which are taught so far. So we started our Maxwell's equation with mathematical preliminaries. So this video is the mathematical preliminaries, the main concepts which we dealt with, mathematical concepts which we dealt. I think you already know. Let me just make a brief review of this. So physical quantities are classified into scalars and vectors. As you can see here, there are scalars and there are vectors. What is a scalar? Scalar is something which has only magnitude, and vector is something which has both magnitude and direction. What are the examples of scalar? Temperature, mass, all these things are examples of scalar. Why? Because they are represented by a number. Mass is represented by a number. It could be 1 kg, 2 kg, 3 kg, 4 kg. 1, 2, 3, 4 represent the magnitude, and there is no specific direction attached to it. Same is with temperature. That's why it's called a scalar. What is a vector? Vector is something which has both magnitude and direction, and not only this, there is a third aspect to it, but that's a matter of detail. It must always obey the triangular law of addition. But let's take it to be something which has magnitude and direction. For example, force, that is a vector. Why? Because if you say that at this point there is a 5 Newton force, that is not enough. You have to say in which direction the force is being applied, whether it is in this direction, or that. So a vector is always represented by a bar overhead. This is the magnitude of it. This is the direction, unit vector direction to it. And then we discussed about the vector multiplication. So if you have two vectors a and b, for example, how do you multiply them? There are two ways to multiply them. One, multiplying them and getting a scalar out of it. Scalar is this one, a number out of it, that is called dot product. In three-dimensional space, every vector, suppose that this is vector A, every vector can be decomposed into three. Since it's a three-dimensional space, it can be decomposed into three components. Ax is the x component, means the component of this vector along x axis. This is component of this vector along y axis. This is component. So it is usually written like this. If you have second vector, it will be written like this. We define a dot b as magnitude of a, magnitude of b into cos of the angle between them. If a and b are these two vectors, it is the cosine of the angle between them. So what will we get? A, that is the magnitude of a. How do you calculate magnitude of a? If a is the vector, this is how we calculate the magnitude. So magnitude of a is a number, magnitude of b is a number, cos theta is also a number. So what will you get? You are going to get a number which will be a scalar. That's why this product is called scalar product. So if there are two I, j and k are, as you know, they are the unit vectors in x, y and z direction. So I dot I, j dot j and k dot k, according to this law, will survive. Every other cross component will vanish. So a dot b is given as ax bx, ay by plus az bz. This is one way of doing that. This is called the scalar product. What is the second one? If you have two vectors, how to get a vector out of it? Okay, that is what is known as a vector product. And how do you do it? Magnitude of first vector, magnitude of second vector, sine of the angle theta. I told you why this has to be cos and why this has to be sine. I am not going to discuss it now. We have elaborated this on the class. So this is the magnitude part of it. What will be the direction part of it? How do you assign a direction? Not that this has a direction by itself. You are assigning a direction. How are you going to assign the direction? It is called right hand screw rule. What is this right hand screw rule? So if you imagine a right hand screw which has grooves like this, which are moving from left to right. If you turn this screw, if this is vector A and vector B, let's say this is vector A and vector B, imagine a right hand screw which is sitting here. Okay, when you turn the screw from A to B, in which direction the tip advances, that will be the direction of the cross product. And if this is the direction in which tip advances, n will be given that direction. So this has how do you compute it? How do you compute the whole thing? It is computed like, so if this is vector A, this is vector B, A cross B is computed as AB sin theta, which is the magnitude, and n is the direction. According to right hand screw rule, this is the direction, and you are going to compute the cross product like you compute the determinant. I told you in the class that what is the relation between cross product and the determinant. Actually, I told you how it signifies the area, how determinant is something which will tell you the area of parallelogram and all those things we discussed. I am not going to elaborate on that. Next concept which we discussed was the field. What is a field? Field comes in two varieties, scalar field and a vector field. What is a field? It is the region of space in which each point has a value. If it has only magnitude to it, it is called a scalar field, because scalar is something which has only magnitude. If each point takes a magnitude and as well as a direction, then that is called a vector field. For example, take temperature. This is a scalar field. This is a scalar field because each point, suppose that this is there, here the temperature is T1, T2, T3, T4. Continuously it is varying in the region of space, and since it is associated only with a number, this is what is known as a scalar field. Vector field is something like this. And what is the example of a vector field? It is the wind velocity. Okay, not only you have to assign at each point what is the speed with which the wind is blowing, you have to also assign a direction to it. So here it might be like this, here it might be like this, here it might be like this. So each point in this region of space has both magnitude and a direction. This is what is known as a vector field. We had discussed regarding this in elaboration. That's why I'm not going to elaborate on this. So this is the next concept which we discussed. Finally, regarding this, we had discussed a concept which is called an operator. What is an operator? Technically, operator can be very rigorously defined, but for our purpose, it is sufficient to say an operator is something which has no value by itself. For example, square root is an operator. What is the value of square root? Square root by itself does not have any value. It is only when it is fed into an argument. So this is called an argument. When something is fed into the square root, it will spit out a value. So operator is something which acts on something and gives a value. By itself, it does not have a value. So square root is one such operator. D by dx is one such operator. There is no value unless you have augment it with an argument. This is what is known as a operator. There are two kinds of operators. One which gives you a scalar, one which gives you a vector. So this is and the most useful operator for our purpose is what is known as a differential or del operator. This is also called nabla. How are we going to define it? This is defined as del by del x into I, del by into j, del by del z into k. Okay, this is by definition. Why are we doing this? Because lot of the physical content can be very, very in capsule. This can be stuffed into this. That is why this is a very, very powerful powerful mathematical tool which is used. Vector calculus is a very, very powerful mathematical tool which is used to describe fields, and that is what we are going to do. Okay, so now with this, what are the operations we can do? We can do a gradient, divergence, and curl. I also derived how these things come about, so I'm not going to do this. Just to say that what are these things? For example, okay, first let's take up gradient. Gradient is the first one. And what is a gradient? Gradient is if you take this vector operator and operate it on a scalar function, for example, or a scalar field. What is a scalar field? As I told you, each point is represented by a number. For example, at any point phi, if the value taken at that point is x square plus y plus z square, since when you evaluate it at any point, let it be 1, 1, 1. What will be the value of this? 1 square plus 1 plus 1, which will be 3. If it is 2, 2, 2, this will be 4 plus 2 plus 4. This will be 10. So each point takes a value. This is called a scalar field. So when you feed in this to this operator, please remember there is no dot, there is no cross. This is a vector operator. It acts on this. There is a partial differentiation here. So what it must give? This is partial differentiation with respect to x. That's why only x component gets differentiated here. So this one gets differentiated. Here only y gets differentiated, other two will go to 0. Here only z gets differentiated. So it is the gradient of any scalar function. Remember, gradient is defined only for a scalar function. When it operates on a scalar function, then what you are going to get is nothing but this. This is how gradient is defined. And what is the physical significance of the gradient? The physical significance of the gradient is it gives you the maximum rate of change of any function like this, any scalar function like this, in a direction which is normal to the surface at the point under consideration. If you are taking the divergence at, let's say, 1, 1, 1, it will give you the maximum rate of change of that parallel to that. This is what gradient is. And gradient, in colloquial language, gradient is nothing but slope. So this is the other name of slope. Okay, so this is what gradient is. The second function which we can do is, now gradient takes in a scalar function, scalar field or a scalar function, and makes it a vector. You see, gradient of a scalar function becomes a vector. Now if you have a vector field itself, there are two things you can do with this. Since this is also a vector, this is also a vector, you can either take a dot product, you can either take a cross product. If you take a dot product, what will happen? This is the definition of psi. This is the definition of del. When it is dotted with this, please remember, when in dot product, I dot I will be 1, I dot j will cancel out, all the cross terms will cancel out, and del dot a is defined as, it is simply, and since you are taking the dot product, it must be a scalar. It is partial differentiation with respect to x of ax. It is the x component of the vector. So del ay by ay, del ay by y, and this is del az by z. So what it will result? It will result in a number. If p is your point under consideration, then you will get some equation, and if you put in the values of p, x, y, z, then you are going to end up with a number. And what is the physical significance of this? This is the most important thing. As the name itself suggests, that divergence operator tells whether there is a positive divergence or a negative divergence or a zero divergence. What do you mean by a positive divergence? Suppose that this is point p which is under consideration. If something is diverging out of this point, then that is what is known as, if this number is positive, then that means the point under consideration is the source. It is radiating radiating some lines of force in the physical context, or it is radiating some vector. That's why this is called a source. If it is negative, all the vector lines are coming into that. This is called a sink. Suppose that this is 0, then it is neither generating anything nor sucking in anything. That is why this is called a solenoidal thing. This is called a solenoidal field. So this is source, sink, and solenoid based upon whether this value is positive, negative, or 0. The third thing which we can do, and which has huge physical ramifications, is curl of this vector field. When you take the curl of the field, there is a cross product. How do you compute it? In the same way you compute A cross B. Once again, this can be a 0, it can be non-zero. What happens if it is 0? Positive and negative has to do with whether it is clockwise or anti-clockwise. But if it is positive or negative, what does it mean? It only means that if P is the point under consideration, the vectors are rotating around this point. Curl means something which it is also called rotation. This curl has another name. This is also called rotation of E. What does it mean? The point under consideration, whether in the field of vectors, whether there is a circulation around that point or not. So if this is non-zero, then there is certainly a circulation. If it is zero, then it is parallel. This is what curl would mean. So these three are the operators which are very, very important as far as our field, describing the field in terms of mathematics are concerned. So to summarize, gradient of a scalar function gives you the it is defined like this. Maximum rate of change is what it will give in a direction normal to the surface. This tells you whether the point under consideration is a source or a sink or a solenoid. This tells you whether there is a rotation of vector around that point or not. And the last aspect which we have touched upon as a part of mathematical basics of this is what are known as integrals. Vector integrals are line integral, surface integral, and volume integral. So what is this line, surface, and volume? As you know, so if this is the vector field which is given by A, suppose you want to travel travel from this point to this point in this field. Okay, so this is a vector field. Each point has one magnitude and direction attached to this. If you take this path, okay, so then the line integral is the function along the line. Okay, so line integral is defined as, if you take the differential path, if you take a very small infinitesimal path, dot it with this vector field A, this is how it is defined. I will give you a very physical example. If you take this F to be this vector field to be the force field, and if this distance is the small distance, and if you generalize it between this is F dot dl, what does it mean? It means work. It is the total work done in moving a particle or moving something from this point to this point. That is what a line integral is. This surface generalization of that would be what is known as a surface integral. It is taken over the surface area. This is the vector field. You choose any small surface area, you generalize it to the whole surface. This is what is known as a surface integral. We have discussed all these concepts in detail in the class, so I am not going to dilate on these things now, because this is a review video. Same thing. If volume integral, it is the three-dimensional domain generalization of the same thing. Suppose that there is a charged surface. You know that the charge density, what is charge density? Charge density is dq. Density is usually mass by volume. Charge density is charge by volume. If this is the small volume, then if you want to find out the whole, what is the amount of charge in the whole surface, then you have to do rho v is the charge density, dv is the volume of this elementary volume of this small box. If you want to generalize it to the whole this one, then you have to take a volume integral so that you can find this. And one more thing, if the path between these two is closed, then it is called a closed integral, closed line integral. There is this sign is indicative of that. If the surface is closed, then it is indicative of this, and volume is anyway already always closed, so it doesn't matter whether you put a ring or not. This is always, volumes are always closed. There are two general results which I will just mention, and we have derived this. This is a general theorem, but we will derive it in the context of electric field when we go to the physics part of it. But there are two general results called Gauss divergence theorem and Stokes theorem, which are very, very important. And what they do is, they will relate surface. Gauss divergence theorem relates surface integral to the volume integral, of course along the closed path surface integral to the volume integral, and Stokes theorem relates closed path surface integral, closed surface integral to the closed line integral. And this is true for any vector. Okay, so it reads as this: the surface integral of vector A with small elementary area, when you generalize it, that is equal to the divergence of, I should have written A here. So divergence of the same vector along the volume, and Stokes theorem says the rotation of any vector F, if you take it along the small surface and generalize it to the whole surface, that is equal to the line integral of F dot dl. These are the general results which will be very, very helpful in stuffing the physical content in this mathematical This is the language in which field theory speaks. So in the next review video, we will review what are all the physical concepts which we have learned so far, so that we can move forward in the next video. Thank you everyone for hearing.